I'm going to speak on the contributions of Indians to combinatorics, especially of the ancient text of the Piṅgala's Chandas-sastra, which is a text of prosody. So this is roughly the outline of my talk. Combinatorics is a branch of mathematics which deals with enumeration and counting of combinations of various entities. Such techniques were developed in India in the context of Ayurveda, that's medicine, Chandas, that's prosody, Sangita, music, and of course mathematics, and even in other disciplines such as architecture. I will mainly speak on combinatorics of the what are called the syllabic meters. I will explain what it is. In Piṅgala's Chandas-sastra, which was a text written around 300 BCE. Mainly the combinatory ideas are contained in certain tools known as Dhara, which is making an enumeration of all metrical forms, the prosodial forms of young syllables, then finding out the total number of them, then finding out which prosodial form is in which place in that enumeration that we have made by our rule. Like that, various combinatorial ideas have been discussed in Piṅgala's Chandas-sastra. I will in the end briefly touch upon combinatorics of Matra Vritas, what are known as Moric meters. I will explain what they are when it comes. This is the larger timeline of development of combinatorics in India. The left column is Chandas, that is prosody, that is the science of meters in poetry. It starts with Piṅgala around 300 BCE, then comes to Janashraya and Virahanka in 600 of the Common Era. Halayuda, who wrote a commentary on Piṅgala's sutras in 950. Kedarabhatta, who wrote a very famous text called Vritta Ratnakara. Gopala, who is a commentator of Virahanka's work. Hemachandra, who wrote works on several subjects, including prosody. Prakrita Piṅgala is a text in Prakrit. Virahanka's text is also in Prakrit. Then it goes up to Damodara and Narayana Bhatta in 16th century. In music also, there is a continuous history of study of combinatorics. Starts with Bharata's Natya-shastra itself, which also mentions Piṅgala's ideas. So Bharata postdates Piṅgala. Parshvadeva, Shangadeva, the author of the very famous text Sangita Ratnakara. Simha-Bhupala is a commentator of Shangadeva. This music tradition, especially the combinatorics of musical rhythms, goes up to our contemporary period. The Charaka Sushruta Samhitas date back to perhaps 600 BC or earlier. The current versions may be dated to around 300 BCE. The Sushruta Samhita has some combinatorical ideas on the various rasas and how they can be mixed. Varahamihira discusses the combinatorics of perfumes. Brahmagupta mathematical text has a chapter, astronomical text, Brahmasputa Siddhanta has a chapter on Chandas Chityuttaradhyaya. Sridhara and Mahavira wrote mathematics text where combinatorics is discussed. Bhaskaracharya, the famous author of Lilavati, has the last chapter of his works is on Ankapasha, which is combinatorics. The greatest contributions came from Narayana Pandita, who also wrote a chapter on Ankapasha or combinatorics in his 14th century work, Ganita Kaumi. Now, before going into discussing what Piṅgala did, we have to see the basic terminology of Sanskrit or prosody in all Indian languages. A syllable or an akshara is a vowel or a vowel with one or more consonants, like ya, shtihi, shra, things like that. These are all syllables. A syllable is lagu if it has a short vowel. Now, even a short syllable will be a guru. Guru is a heavy syllable, lagu is a light syllable. This is the definition of a light syllable. That's a consonant with a short vowel. But even a consonant with a short vowel will have to be considered guru if it is followed by a samyukta akshara, conjunct consonant. I will explain it in a second. An anuswara or a visarga. And all other syllables are heavy. So we will explain this lagu and guru symbol is the classification of syllables, which is at the basis of the science of prosody in this following example. This is the first verse of Kalidasa's Abhigyana Shakuntalam. Ya Srishtis, Rashturadhya, Bhati Vidhivutam, Ya Havir, Yacha Hotri. These are the various syllables in this first quarter, first pada of Kalidasa, first verse in Abhigyana Shakuntalam. It has 21 syllables. It's in a meter called Sragdhara. First syllable is Ya. This is a Dirgha, so this is a Guru. Second syllable is Sr. This is a Hrasva, but it is followed by a conjunct consonant Shtihi. Therefore, this is also a Guru. Shtihi, since it has a Visarga, is a Guru. Sra is a conjunct consonant, but it is Hrasva, but it is followed by another conjunct consonant. So, any syllable which is prior to a conjunct consonant is a Guru. Shtu is a Lagu. It's a short syllable. Though it's a conjunct consonant, it is not followed by a conjunct consonant. It is a Lagu. Ra is a Dirgha, Guru. Gya is a Dirgha, it's a Guru. Bahati are all Lagu. Vidhihu, they are also Lagu. Tam, it's with Anuswara, it's a Guru. Ya is a Guru. So, this Ya Srishtis Rashturadhya, Bahati Vidhivutam, Ya Havi, Yacha Hotri has 21 syllables and it has this Guru Lagu pattern. Then there are 8 ganas. Every triplet of Lagu and Guru is taken as a gana. Obviously, there are 8 such triplets and they are called Yagana, Ragana, Tagana, Bhagana, Jagana, Sagana, Magana and Nagana. We will not be discussing these ganas later in this talk. This is the words which defines the ganas. Adi Madhya Vasanishu Yarata Yanti Lagavam Bhajasa Gauramam Yanti Manautu Guru Lagavam. And this Ragdhara meter is defined by this verse. Nabhnair Yanam Trayena Trimuni Yati Yuta Sragdhara Kirti Teyam Marabhana and 3 yas. With a yati or a pause after every 7 syllables is Ragdhara. And surprisingly or beautifully, this verse itself is also in Sragdhara meter. Now we will straight away jump to Piṅgala's Chandas-sastra. Piṅgala is a junior contemporary of Panini. Panini is supposed to have flourished in 500 BC. There are many stories of ancient times where Piṅgala and Panini are combined together also. Chandas-sastra comprises of 8 chapters. It's in the Sutra style. It has 315 sutras. It has been commented upon by Halayuda in the 10th century and by Yadava Prakasha in the 11th century. The first chapter deals with definitions. And the very first sutra, Dhi Shvi Stream, defines the Magana. Very interesting mathematical point about Piṅgala's Chandas-sastra is that it is using what is called Bhuta Sankhya system of numeration. That is, a word such as Vasu, there are 8 Vasus. So you use the word Vasu to mean the number 8. This is used in general in Sanskrit literature to denote numbers. They use what is called the Bhuta Sankhya system. Apart from that, we have what is called the Katapayadi system, for which the earliest works come much later, around 4th century, whereas Piṅgala's Chandas-sastra of 3rd century BCE already had the Bhuta Sankhya system. Then Piṅgala goes on to discuss Vedic meters. Like Panini's grammar, Piṅgala's Chandas-sastra has also both the Vedic meters and the classical meters of Sanskrit. 6th and 7th chapters deal with most of the standard meters of Sanskrit poetry. And it's in the 8th chapter that Piṅgala discusses these 6 combinatorial tools that I said right at the beginning in the outline, called Prastara, Sankhya, Nashta, Uddishta. We will explain what each of them are and how Piṅgala does very interesting mathematical study of meters. First is to write down all meters of a particular length. As we see, each metrical form is a sequence of Lagu and Guru, G and L. So it's what can be called by mathematicians as a binary sequence with the 2 kinds of entities in the sequence. A prastara of 1 syllable meters will just look like this. Prastara of 2 syllable meters, there are 4 of them. They are arranged like this. Prastara of 3 syllable meters, there are 8 of them. They are sequentially arranged like this. The rule for sequentially arranging it is given in these 4 sutras. What Piṅgala says is, form a GL pair. Then write that GL pair below itself. Insert on the right G's and L's. Now, this is a recursive rule. Then you should keep doing the same thing. So, the 2-syllable prastara is written below itself and the right hand side is filled with G's and L's. To get a 4-syllable prastara, the 3-syllable prastara, these 8 rows are first written twice, one below the other. And then G's and L's are put in the end. So, this is Piṅgala's rule for prastara. So, this way, all the 2 to the power n metrical forms of n syllables are ordered in a sequence. The top row is all GGG, the last row is all LLL. There is another rule for prastara which is given in a text called Vruttaratnakara, which comes in the 10th century. I will not describe this rule in detail, but the way this rule proceeds is you can be anywhere in prastara, scan from the left, locate the first guru, and below that write a laghu. Bring down the 2 syllables on the right as they are, whatever syllables are to the right of this guru. To the left, you put gurus only. So, for instance, here, LGLL, the row below that, identify the first guru, put a L below that, bring down these 2 L's here, fill up the left side with G. Go on till L's are reached. A very important and interesting property of this prastara is its relation with binary representation of numbers. So, if you set G is equal to 0, L is equal to 1. So, I have rewritten this prastara of 4 syllables with the G as 0, L as 1 here. Then, you take its mirror reflection. That is, 1000 becomes 0001. 1100 becomes 0011. Then, the binary number that comes here is the binary number of the row minus 1. This 11 is binary representation is 3. 100 in binary representation is 4. That is 5 minus 1. This 1010 in binary representation is 10. And you see that is 11 minus 1. So like this, there is a one-to-one correspondence between prastara, the row number of the prastara, and the binary representation of the associated binary sequence. If we put G is equal to 0, L is equal to 1, it was using this that Piṅgala constructed various interesting mathematical problems associated with this prastara. The first mathematical problem is computing 2 to the power n. Piṅgala does it in 4 sutras, and notice that the word shunyam appears, though it appears as a mark only in Piṅgala's sutra. Piṅgala is giving a rule for finding the nth power of a number by a much smaller number of operations than merely multiplying the number by itself. If you want to multiply the number by itself n times, you are doing n multiplications, whereas Piṅgala's algorithm has much smaller number of squarings and multiplications. The rule of Piṅgala, I have stated here, it is based upon these 2, what may be called the power laws, which were very clearly known in Piṅgala's time to the Indian mathematicians. I will explain Piṅgala's rule for taking the power with a simple example. The rule starts like this. Supposing you want to calculate 2 to the power 21. You want to know how many rows are there in the prastara of the 21 syllable meters. The first rule is halve the number and mark 2. If the number cannot be halved, deduct 1 and mark 0. 21 cannot be halved, deduct 1 and mark 0. So you put a mark 0 here. The next rule is proceed like this till you reach 0. So next time you have now 10. 10 can be halved, and so mark 2. So I have put a mark. Now you have 5 here. 5 cannot be halved. Deduct 1 from 5 and then do the halving. Then mark 0. 4 can be halved. Halve it, mark 2. 0, 2, 0, 2. 2 can be halved. Mark 2. 1 cannot be halved. Subtract 1. Mark 0. So this is the sequence of numbers that you get. Sequence of marks. Now you proceed in the reverse. Wherever 0 occurs, you multiply by 2. Wherever 2 occurs, you do a squaring. So 0, 1 into 2. There is a 2, 1 into 2 square. there is another 2, 1 into 2 squared squared. There is a 0, 1 into 2 squared squared into 2. There is a 2, 1 into 2 squared squared squared. And last one is 0. Finally, you will get 2 to the power 21 is 1 into 2 square of the whole thing, into 2 square of the whole thing into 2. So, for 2 to the power 21, Piṅgala's algorithm involves only 3 squarings and 2 multiplications and not 21, but it's a very optimal algorithm for finding the square of a number. And this algorithm was used for summing geometric series in later Indian texts such as Mahavira's Chandas-sastra, etc. Piṅgala's rule also, there are 2 sutras which tell you the sum of a geometric series like this. 1 plus 2 plus 2 squared plus 2 to the power n is 2 to the power n minus 1 minus 1. This formula also appears in Piṅgala's Chandas-sastra. Now there are 2 algorithms needed. One is, you know this prastara for, if you're thinking of 4-syllable meters, these are the 16 rows. Now suppose you don't want to write down all the 16 and I ask you the question, what is the 7th row? Or I ask you the question, what is the row in which GLLG appears? So the first question, GLLG appears, what is the row? Is called the ranking in modern computer science and mathematics or combinatorics. It is called Uddishta. And supposing the question is, what is the 7th row? That is called Nashta. That means you have already written the prastara, but somehow it is lost. You just tell me the 7th row. Piṅgala gives algorithms for both these calculations, for standard procedures for both this, unranking and ranking as it is called in today's combinatorics. And he gives them basically based upon the relation that we noted earlier between the row number in the prastara and the binary representation of that number. So I will just explain Piṅgala's algorithm for Uddishta. The Nashta algorithm is similar to the Sankhya algorithm, so I will not explain it in detail. The Uddishta algorithm is that you are given the metrical form, tell me which row it appears. So for that, Piṅgala's algorithm is in 2 sutras and it can be translated like this. Pratilomaganam dvidladhyam tato gyekam jakhyat. Start with number 1, double it when L is encountered, double it and reduce by 1 when a G is encountered. So you scan the pattern from the right. There is another alternative algorithm. I'll come back to it after 1 minute. But let me do an example for this. Supposing I want to find out what is the row number for the pattern LG in 4-syllable prastara. So we start with 1. Since a G appears, nothing needs to be done. You have to come till the first L. Now you have a L here. You have to multiply by 2. Then there is a G. When we find a G in the middle, we multiply the previous number by 2 and subtract 1. Finally, you have a L. You multiply by 2. So it occurs in the 6th row. We can go back and check that it actually occurs in the LG occurs in the 6th row of the prastara. There is another method given by Kedara Bhatta, which is more transparently related to binary representation. So I will tell you. It says place 1 on the top of the leftmost syllable of the given metrical pattern. Double it at each step while moving right. Sum the numbers above L and add 1 to obtain the row number. So let us do the same example. LG. Put 1 above the first Laghu or Guru, whatever it is. Double it at each step. 1 into 2, 2 squared, 2 cubed. Add the numbers above the Laghus. That is 1 and 2 square are added. To the entire thing, add 1 more, you get 6. So these are the 2 algorithms by which you can immediately find out the pattern LG is in the 6th row of the prastara. This is a small prastara, 4-syllable, but if you have prastara of 21 syllables like Dhara, where it will actually in the prastara can be found out very easily by these kinds of algorithms. The last rule given by Piṅgala was a very interesting rule. How many metrical patterns are there of n syllables which contain r gurus, where r is any integer 1, 2, 3, 4, etc. up to n. The same question can be posed: how many metrical patterns are there in a meter of n syllables which have r laghus, for instance? Piṅgala gives this answer in just one line, and various earlier sutras have to be used to understand this. The explanation is provided by Halayuga, the 10th century commentator, who calls, Piṅgala asks you to construct a Meru Prastara. Halayuga calls that the tabular form as Meru Prastara. So I will explain the Meru of Halayuga. You start with one cell with 1. Below that one cell, you write 2 cells which overlap with the first cell. Similarly, below the 2 cells, you write 3 cells which overlap with the cells above. Similarly, you write 4 cells. Now, the rule for filling each of them is any number is filled by the sum of the 2 numbers above it. That is the meaning of Pare Purnam. And so 3 occurs here, it is sum of 1 and 2. 4 occurs here, it is sum of 3 and 1. 6 occurs here, it is sum of 3 and 3. As you can see, these are the well-known binomial coefficients. And in fact, this triangle became very famous. It was rediscovered in Islamic mathematics in 10th century, in China around 13th century, and in Europe first by Stiefel, and then a treatise was written on it by Pascal. So it is today called the Pascal triangle based upon his treatise. And this relation, each number is sum of the 2 numbers above, is nothing but this relation between the binomial recurrence relation between the binomial coefficient. That is at the heart of Piṅgala's Meru. There is a later version of this Meru that Varahamihira constructed. He was trying to work out from 16 different perfumes, if 4 perfumes are selected, how many variations are possible, and that is 16C4, that is 1820. Varahamihira asks you to construct a Meru like this, which is a rotation of Piṅgala's Meru. This 1, 1, 1, 1, 1, 1, 2, 3, 4, 5. So this 1, 2, 3, 4, 5 is the first row of Varahamihira, first column of Varahamihira's Meru. It says in the first column you put the integers. In the second column you put the sum of integers. So 3 is 1 plus 2, 6 is 1 plus 2 plus 3, 10 is 1 plus 2 plus 3 plus 4. And in the next column you write the sum of the previous sums. 1 plus 3 is 4, 1 plus 3 plus 6 is 10. These are what are well known as triangular numbers. Now, Varahamihira says NCR can be found out going to the nth column and the rth row in it. And this construction of Varahamihira is based upon just the extension of the Piṅgala's. If you go on recursively replace this n minus 1 CR by the same rule, you will get this summation. This is a well-known rule. This was first discovered in Europe by Fermat, but this is the rule at the heart of Varahamihira's Meru. It was explicitly stated as Vara Sankalita formula, repeated summation formula by Narayana Pandita in his Ganita Kaumudi, which I mentioned. Now, this is a very interesting Meru, as you can see. It's a very simple way of calculating. Every time you don't need to sum everything. 35 is obtained by summing just 10 and 50, the previous 20 and 50, the previous entry and the previous one. 70 is 35 plus 35. 210 is 126 plus 84. Today we know this formula. NCR is n factorial by n minus r factorial into r factorial. This was first mentioned in the Patiganita of Sridhara and in the Ganita Sara Sangraha of Mahavira. I will not say much about Matra Vrittas. I think the time is running short. I will tell you the central point. You assign value 1 to Laghu and 2 to Guru. Roughly sort of the time it may take to pronounce a light syllable and a heavy syllable. Then LG, this metrical pattern will have 8 matras. In music it is called matra kalas. So these are called moric meters. A matra in Latin is called a mora. So Piṅgala is very briefly touched upon them, but the first work to give it in detail is the work called Vritta Jati Samuchaya Virahamka, written in 600. It is in Prakrita. Its commentary I mentioned was written by Gopala in 11th century. It discusses both the Prastara and the Sankhya Virahanka's work. I will quickly tell you what are the prastaras of Matra Vrittas. They proceed on the same rule, the way Vrittaratnakara rule proceeded. There are two ways of constructing. You construct first the Matra Prastara for one Matra and two Matras, then put them one below the other. This L is put here, this GLL is put here. On the right side, you put a G for this, L for this. Similarly, 4 Matra Prastara is constructed by putting a 2 Matra Prastara here, a 3 Matra Prastara here, put 2 G's on the right side, 3 L's on the right side. Similarly, 5 Matra Prastara can be constructed from 3 Matra Prastara and 4 Matra Prastara. So it was this thing that Virahanka noticed. So he said the number of rows in the Prastara of all those metrical forms corresponding to a given Matra is the sum of the number of rows in the metrical forms corresponding to the 1 Matra below and 2 Matras below. So Sn is Sn minus 1 plus Sn minus 2. You can immediately recognize, given that S1 is 1 and S2 is 2, that you get the sequence of numbers 1, 1, 2, 1 plus 2, 3, 2 plus 3, 5, 3 plus 5, 8. Today we know these numbers as Fibonacci numbers, and these were originally discussed by Virahanka and later explicitly written down by Gopala. Virahanka gave the rule for all these prastaras, which you read in you. Today we know that many properties of Matra Vrittas are dependent on these Virahanka Fibonacci numbers. There is a very interesting work called Ganita Kaumudi in 14th century, which deals extensively with combinations, combinatorics. And here is a praise of this work by Donald Knuth, who says that it anticipated developments of the rest of the world by several hundred years. It's indeed true. Every result in Narayan Pandita on combinatorics has to be discovered in 17th, 18th, and 19th century, later mathematicians. Here is a verse of Bhaskara's Leelavati and a verse of Ganita Kaumudi on combinatorics, which says that this is a very interesting branch of mathematics, which does not involve calculations using multiplications or divisions, squares or cubes, as in astronomy, etc. But it is very tough, and therefore a mathematician who is conceited is bound to fall while solving such problems. Only good mathematicians can handle Anka Pasha or combinatorics. This was indeed a glorious subject which has had a glorious history in Indian mathematics. These are some of the references for the discussion of history of combinatorics in India from Piṅgala to modern times. Thank you very much.